In this video, we describe a client-server architecture to build a distributed system to share small UAV telemetry information over a network and a prototype implementation of such a system. Small UAVs today only communicate with their pilot and the GCS, that is the ground control station application, running on the pilot's PC or tablet. No mechanism exists for small UAVs to share telemetry information such as position, heading, altitude, etc. with other small UAV pilots, and more importantly, with federal, state, and local authorities tasked with maintaining the security of the national airspace system. For example, an air traffic controller has no way of determining how many small UAVs are operating within a given search radius of an airport. The invisibility of small UAVs to those not directly flying them has led to a justified fear of a small UAV inadvertently violating airspace regulations, or even worse, coming in the way of a manned airplane and causing an accident. This concern has resulted in overly draconian restrictions on where and how high small UAVs can be operated. We propose a client-server architecture to create a distributed system to disseminate small UAV telemetry information over a network where it can be easily shared by other authorized pilots and aviation law enforcement in a robust, secure, and efficient manner. In our system, GCSs will send selected telemetry information over an internet connection to a server that accepts and services connections from multiple GCS and provides telemetry data slices to clients as requested. A server can also implement secondary operations such as telemetry data storage, client authorization, data analytics, history, and so on. A client enables a user to submit search queries to the server. For example, an air traffic controller running our client could say, "Show me all UAVs flying within 5 miles of my airport," and receive a list of all small UAVs that meet the search criteria. The client can also implement dashboards for visualizing the telemetry information. For example, an instrument dashboard for visualizing the orientation, heading, and altitude, and a map to show the position of the small UAVs. Let us now consider some important features of our system. Our system is completely modular. The major components of the system, the device, server, and the client, communicate with each other through messages and can be implemented in different programming languages. For example, the server could be implemented in C++, as in our prototype implementation, or using technologies such as Node.js. There is no single point of failure. With the exception of the server, any component in our system can fail without affecting other parts of the system. The system can be made robust even to a server failure by having multiple server instances to introduce redundancy. The client and the devices will simply connect to another server instance in case their current server instance fails. Data logging. Our system provides a natural way to save user-specific flight logs on a central database and makes it easy to share these logs with UAV manufacturers in case of a malfunction and with law enforcement agencies to verify compliance with aviation regulations. The modular nature of our system also makes it highly extensible. Users and third-party application developers can develop plugins to process particular data embedded in flight logs. For example, geotagging pictures taken by a camera on board the UAV from latitude and longitude information embedded in flight logs, which is an important task in survey applications. Before we discuss other features of our system, let's take a look at our prototype implementation. In our prototype implementation, we use two drone mockups that have on board most of the sensors that are used on a real small UAV. Our mockup has a 10 degree of freedom IMU with a 3-axis accelerometer, gyroscope, magnetometer, temperature sensor, an air pressure sensor, and a U-Blox Neo 6M GPS unit. These sensors are connected to an Arduino Mega over I2C serial connections. We have also written a prototype firmware running on the Arduino consisting of a scheduler and a DCM sensor fusion algorithm to produce position, that is the latitude and longitude, orientation, that is the yaw, pitch, and roll, altitude, heading, and temperature estimates from the raw sensor values. These estimates are encoded into the Mavlink format and transmitted to our workstation over a radio link. Our mockup uses an XB radio running at 115,200 baud, while the other mockup uses a 3DR 915 megahertz radio that is also used on the Iris Plus drone at 57,600 baud. The Mavlink encoded telemetry data is received by the XB and the 3DR radio receiver connected to two different serial ports on our workstation. The next piece of the system is a program that we call device. This program is responsible for receiving telemetry information over a communication port, applying any necessary decoding, and sending it to a server in a predetermined format. Our device program is written in C++ and sends the decoded telemetry information as strings to the server over a WebSocket connection. For example, GPS information is sent by concatenating latitude, longitude, number of satellites, horizontal dilution or precision, etc. into a space-separated string. Note that we prepend each message string by the device ID so the server can distinguish between messages sent by different devices. The device program could be different for different UAVs, as different UAV vendors could use different format to send their telemetry data. Thus, the device program insulates the downstream system components from variations in UAV-specific telemetry encoding. The next piece is a program called server. In our implementation, the server is a multi-threaded application implemented in C++ that accepts and services WebSocket connections from various devices and clients. The server maintains a history of telemetry data sent by different devices and sends this data to clients at the client-specified data rate. Only fresh telemetry data is sent to the clients in order to reduce network load. This is important because different pieces of telemetry information is sent at different rates. For example, orientation estimates are typically sent many times a second, while GPS coordinates might only be sent once a second. The last and most visible piece is the client. A client is a program that receives telemetry data from the server and presents it to the user through suitable visualizations. For example, an instrument dashboard to visualize orientation, heading, altitude, and a map to see the position of the UAV. A client can also have panels for mission planning, setting various UAV parameters, and so on. Our client is written entirely in HTML5 and JavaScript and can run on any browser. Let us now see our system in action. Let's first recall that our system consists of three components: device, which is a program that connects to a serial port and receives the telemetry information being sent by a small UAV on the serial port, applies any necessary decoding, and then sends the decoded telemetry information to a server. A server is a program that accepts and receives connections from multiple devices and clients. And client is a program that receives the telemetry information from a server and implements appropriate visualizations for the telemetry data. We will first run our server program that listens for incoming WebSocket connections on port 9002. We will first run the server locally and then on a remote computer. Our server executable is called GCS_server, and it reports the number of devices and clients connected to it. Since we haven't run a device program yet, it reports 0 for each. Let's now go ahead and run our first device program. This device program will receive the telemetry information being sent by one of the UAV mockups on port 19 at baud 115200, decode the telemetry information, and then send it to the server that is running on the local host at port 9002. It also outputs the telemetry information that it receives, and if I now go back to the server, I can see that it reports one device connected. Let's take a look at the client now. So a client in our case is written entirely in HTML5 and JavaScript, so it can run on any modern browser that supports WebSockets and WebGL. Let's recall, however, that we do not impose any technical requirements on what software stack is used to implement the device server and the client. They communicate with each other solely through WebSocket connections and can be implemented using any software framework. For example, the server could be implemented using technologies such as Node.js, and the client could be implemented in Qt. Now, if our client shows us all the UAVs that satisfy the user search query, which is entered in this web form on the left sidebar. Since I'm located in Arlington, Virginia, and this video is being recorded from the living room in my apartment, I'm using my own address. If I change the search query to Arlington, Texas, the system correctly tells me that no devices are found within the specified search radius of 2 kilometers, and it also tells me where the closest device is located, which is my apartment address. If I change the search address back to my apartment address, it shows me the one device that is connected to the server. The position of each UAV is shown by a dot on a map. And there is also an info box that shows us the device ID of this UAV. Another info box on the top left shows more detailed GPS information, such as the number of satellites, the horizontal resolution or precision, and so on. I can also obtain a history of this UAV by right-clicking and opening up a history context menu. And now the server sends me a history of where this UAV has been, and I can zoom in to see the history a little bit better. Even though in this demo the UAV mockup is sitting stationary on my living room floor, so the spread of the dots actually reflects the variation in the GPS position estimates. The device list that you see here is updated continuously. So if I run my second device program, which receives the telemetry information sent by the other drone mockup at 57600 baud, the device list here updated automatically. And if I select the second device, then I will see the telemetry information for that device. Let's now take a look at the instrument panel. So the instrument panel has 4 displays. The first display is a drone model that changes its orientation as I rotate the drone mockup. Let's take a look at that. So here you can see that as I turn the drone mockup, the drone model on the screen moves accordingly. And same thing for the compass. If I change the heading of the mockup, the compass rotates to reflect the new heading. And then there is also an altimeter and a display that shows the temperature and the altitude. The instrument panel is implemented using WebGL, which most modern browsers now have a good support for. WebGL can be used to implement some beautiful dynamic displays efficiently. Let's now open up the client in another tab. And let's change the data rate, which is by default set to 15 Hertz to 1 Hertz. And now so we are basically asking the server to send us the updates for the telemetry information once a second instead of 15 times a second. And you can see the the instrument panel now updates much less frequently. But if I go back to the previous tab, you can see that the data rate there is still 15 Hertz. So the changes that I make in one tab has no effect on the client running in the other tab, and that is because the two views maintain a separate connection with the server. So it's easy to see how this technique can be used to implement separate views for the telemetry data, mission planning, setting UAV parameters, and so on. Now incidentally, if I go back to the server output log, I will see that it now reports 2 devices and 2 clients corresponding to the 2 browser tabs that we just opened. So far we have been running the server on our local computer. Let's now try running the server on a remote computer. So we have already uploaded a server executable compiled against Linux networking libraries on a remote computer hosted on DigitalOcean. We will now first of all run that server. which correctly reports 0 devices and 0 clients connected, because the devices that we are running are sending their output to the local server. So let's stop these devices and ask them to send their output to the remote server, which is located at 104.131.41.226. So you can see how easy it is to direct the device output and send the telemetry information to a different server. And let's do the same for the other device. And now I'll open up another tab, and instead of connecting to my local server, I will connect to the remote server, and you can see that it now shows me the 2 devices that I just ran. Incidentally, I can also connect to the server using the browser on an iPhone, and I'll be able to see the same client dashboard as I see on my PC. And also note that I'm running the client entirely on the browser. I didn't have to install anything on the phone to see this dashboard. Thus, any authorized internet-connected user can see the orientation, position, and other telemetry data sent by my drone mockups. Let us now consider how our device server client model can be used to implement ground control stations themselves that the user can install on their PC or mobile device. Ground control stations are currently designed as monolithic applications using native application design frameworks such as Qt, making them difficult to extend and port to other platforms. Consider a common ground control station called Mission Planner. I've used Mission Planner extensively and I love it. However, if I want to extend Mission Planner, I'll have to get the source code, figure out how it works, and then try to modify the code and recompile Mission Planner. If I'm using Mission Planner on multiple platforms, I will have to make my code change to the code repositories on all the platforms. So how does one implement a ground control station using a client-server architecture? One way to do so is using frameworks such as Chromium embedded frameworks that allows embedding a web browser engine into an application and develop GUI panels using HTML5 and JavaScript. In this design, the GCS will be split into 3 components: a device that receives telemetry information sent by the UAV over a serial port and performs any necessary decoding. The device then sends the telemetry data to a server that is running as a separate process or is part of the GCS application itself. The server would then supply the telemetry data to different client views, implementing different types of visualization. Some of these are similar to what we have already seen. For example, an instrument panel dashboard consisting of a drone mockup showing the orientation, compass showing the current heading, and so on. And also a map view showing the position of the UAV on a map. A GCS can also have additional views for planning missions, setting UAV parameters, etc. A major benefit of this design is extensibility. End users can now add application-specific visualizations. For example, a visualization to see which areas have been covered in a survey or to draw complex routes for automated UAV operations. This can be done without having to touch the device or the server code. This is in contrast to current GCS applications, which have to be recompiled from source after making any modifications. Let's consider one use case of a GCS built using this architecture. In this use case, a remote pilot can view the real-time telemetry information being sent by the pilot GCS either over an internet connection or over a local area network by directly connecting to the GCS's server. This can be useful for a survey application where the pilot can focus on flying this small UAV, while the remote co-pilot can ensure that the small UAV flies over all parts of the survey area and that there are no survey gaps. In our experience conducting surveys, this functionality can be very important when automated mission flying is not possible due to the presence of tall structures such as trees and lampposts. Another application of this use case is for real-time analysis of sensor flight control data sent by a small UAV. The pilot can focus on flying the UAV while a remote analyst can view detailed real-time plots of various sensor flight control data for debugging or diagnostics. So, to recap, in this video, we discussed a client-server based architecture to create a distributed system for sharing small UAV telemetry information over a network. We saw a demonstration of a working prototype of a system built using this architecture. And finally, we discussed how this architecture can be used to implement ground control stations themselves. Thank you for watching.